everyone. This is the June event of Ithaca Fest. And today we have 3 speakers as usual. And the first speaker of the day will be Luigi Santocanale, and his talk will be about complete congruences of completely distributive lattices. Luigi, whenever you're ready, you can take the stage.
Okay, I'm almost ready. I'm never ready, but I'll take the stage anyway. Thanks to all the organizers for proposing me to give this talk. And I decided to present this work that we have completed recently with Cameron Calca, and for which there is we have submitted to the conference Ramix. It will appear on Ramix. Let me do advertising for Ramix. If you have nice things, send to relational and algebraic methods in computer science. Do not hesitate. Come in Prague this August to see the conference. Okay, now I can really start. So, okay, advance. What's up? Okay, so more or less, I want to tell you first where my interest for this completely distributive lattices comes from. It's easy to talk more on posets than on categories, okay? So, but there are some categorical things that are very important in what I'm going to say. So, I was studying binomial and multinomial lattices in combinatorics. What are they? They are paths that goes from one side of the plane to another side. They are discrete. And what it's interesting is that the congruences of these finite lattices behave like some kind of patching in 2 dimensions. So a path is something in dimension 1, and here there is a joint irreducible which acts as a cell where we have put some a piece of well, a little cube, and this so a congruence class is essentially made by a set of these squares, not cubes, okay, in dimension 2. So, for example, here there is the blue path that I can convert. I can put equivalent to the path that goes up to the square, and then to the path to that goes up to the square. And if you see, so here is a piece of the Hasse diagram of this lattice. So here is the blue path, which is composed by east, east, north, east, east, north, east, north path. And then this northeast path becomes equivalent to these 2 east-north steps are equivalent to making here a northeast step. So there was something that in the combinatorics, in the lattice theory, that appeared very much similar to what people were doing with directed homotopy theory for the modeling of concurrent computations. And so at some point, Cameron Calca came in Marseille, and he's an expert of homotopy, directed homotopy theory. So I asked him, now you go ahead and look what are the relation between lattice theory and directed homotopies. Okay, so he did everything in the combinatorial way, but what I'm going to present today, okay, let me see if is okay, it is a continuous approach to all this. These discrete grids, I can embed everything in to the grid, essentially into the 0, 1, interval 0 to 1 square. And even here, I can talk about paths. So what is a path? It is a continuous map from the, let's call it the unit interval to the square of it. So imagine this is parameterized, but relates the 0, this point to this point. And we consider monotone continuous paths, okay? Or even better, when I look this kind of diagram, I consider the image, okay? I'm not interested into the parameterizations. And then there are, if I consider these things, there are various bijections of various way of seeing of it. For example, if you take a maximal complete chain as a sublattice of this complete lattice, okay, these are in bijection with the images of these paths. Okay, there is another. Let me try to. Okay, can you see now?
Yes.
Okay, I put in full screen. So another bijection is with sup-preserving maps from here to here. So just to understand why, just draw a sup-preserving map, draw the graph of this map. So it is increasing, it might have discontinuity points, and it is preserving if it is continuous from the left, and it is preserving if it is continuous from the right. But what you do is these discontinuity points, you add the intervals, and then you have a complete chain, which you can think as the image of a path. Okay, then on this kind of objects, you have an order, you have an ordering. So the blue path is below the red path because the red path is always on the left and above the blue path, okay? And this is a very simple ordering. If you think these paths as complete, as a sup-preserving maps from the unit interval to itself, then this is just the point-wise ordering. So at each point, at each time here, the the value of the red map is bigger than the value of the blue map. Okay, so this ordering is is actually a completely distributive lattice. Okay, let me recall what is completely distributivity for a complete lattice. So there is this big exchange of infima with suprema, and so it is a wide generalization of the distributive law. Okay, so in particular, this complete distributive every completely distributive lattice, the binary meet commutes with the infinite suprema, so it is a complete Heyting algebra or a frame. Okay. Okay, now let me tell what I showed before. It is, moreover, a quantale. It is a Girard quantale, and as an order, so this this ordering that I showed before between paths, it is a completely distributive lattice, so it satisfies that. I don't want to bore you with proofs, but I would like to give you an idea of what's going on behind my statements. First of all, I'm considering the category of complete lattices and sup-preserving maps, and this is a well-known star-autonomous category, so in particular is monoidal, symmetrically monoidal closed. So then what I just told you is that this QD of V is just the sup-preserving maps from the unit interval from itself. So it is the internal Hom in it is an internal Hom between the same object. And as such, it is a standard monoid in the monoidal closed category sup. Okay, and a monoid in such a category is actually a quantale. Okay, now the point is that let me this unit interval 0 to 1 is a chain. It is a complete lattice, so it is a completely distributive lattice, okay, because it is a chain. And there is a result that I don't know in which measure is due to Krumle-Paseka. I don't know whether Egger has contributed on that, but it appears in a chapter by Krumle-Paseka, and which say that this internal monoid is a Girard quantale, so essentially it is a star autonomous as a poset. It is a complete poset, and moreover it is a standard autonomous if and only if the object this lattice, complete lattice, is completely distributive. Okay, I got interested and I saw this also works for Frobenius quantales, for those among them who knows it. Okay, so now an interesting point is that the completely distributive lattices are exactly the nuclear object in this category of complete lattice and sup-preserving maps. And the nuclear, so here you have in sup, the unit of the tensor is also a dualizing element. So you have a canonical map of this kind. So this is the dual of a complete lattice. It is the op, and there is a canonical map into the internal op. And so the nuclear objects are exactly those for which this mixed map is invertible. Okay, so the last thing that I want to observe is that the nuclear objects in a symmetric monoidal closed category are sort of a reflection, okay? So if you collect all of these nuclear objects, with the same tensor, they form a compact closed category. And so you have that the nuclear objects are closed under the tensors, the internal ohms, the duals, and so on. Okay, so what is the conclusion is that my space of sup-preserving maps from the unity interval to the unity interval is completely distributive. Okay, having said so, let me check from time to time what is the time. Okay, so if this arrives on the web, here there is a bunch of reference that over which I've been working on, under which I took my background on the subject. Okay, so now let's see completely distributed lattice in a completely different way. Let me recall what is Hoffmann-Lawson duality. Okay, for this I need to recall you what are domains, continuous domains, the way below relation. So I take a poset which is suprema of the directed subset. So this is called a domain or a CPO. So in this kind of posets, you consider the way below relation. So X is way below Y if whenever Y is covered by D, okay, and D is directed, then X is less of at least one element of this set. Okay, so this is a generalization of the notion of compact element. So the compact elements are those exactly for which X is way below X. So it is said that X is way below Y. You can say that X is relatively compact to Y. Okay, so let me tell you what is a continuous domain. Okay, okay, this set is the collection of all elements that are way below X. Okay, for a domain to be continuous, you ask that this set is directed, and moreover, it joins to the element. So these are good approximants of each element, for each element. Okay, so, well, let me say that I heard about this kind of theory lots of time, but I got the feeling of what this way below is just recently. So let me tell you what is this. So if you consider the unit interval without the zero, so the way below relation is just the strictly below relation. So this is, has no compact element, but the way below relation works well, meaning that it is a continuous domain. Okay, you have also that the unit interval is with the zero is a continuous domain, where the way below relation is essentially the same. Moreover, zero is a compact element. Okay, why I put in the relation of the two? Because the 0, 1 are exactly the joint prime elements of this complete chain. Okay, now the continuous domains are closed under the product, and the way below relation is just the product of the two. And I'm telling you because I'll consider the joint prime elements of this Q of V, okay, that I presented before, which is essentially a product of this interval 0, 1 without the 0. To see why this is the case, just let me say that a path is join irreducible or join prime, because everything is distributive, if it makes just one turn here. So essentially it's completely determined by this point. Okay, and this point cannot be taken here or here. Okay, it needs to be inside. So it cannot, you cannot have x equal okay, y equal 0 and or x equal 1. Okay. Okay, now let's come back to completely distributive lattices. These are continuous domain, and there is a nice result that I hope I transcribed it properly, that a complete lattice is completely distributive if and only if it is distributive, and both him and its dual are continuous as domains. Okay, there is a nice thing that you can prove about completely distributive lattices, that they are generated by the under suprema by the join prime element. Okay, or and because everything is auto-dual. Okay, so L-op is evidently also a completely distributive lattice. Then they are also generated under meets by the meet prime elements. Okay, in frame theory, you would say that such a lattice, such a frame is spatial. So they are spatial as frame, but also called spatial because they are autodual. Okay, what does it say, the Hoffmann-Lawson duality? Says that for each completely distributed lattice L, the set of joint prime elements is a continuous domain. Given a continuous domain, you can take the downsets that are closed under suprema of directed joints. This make up a completely distributed lattice. And this extends to a categorical duality, because if F is some kind of frame homomorphism, okay, let me say preserve arbitrary infima, but only find suprema, then the left adjoint of this map restricts send joint prime elements to joint prime elements, and it is preserved suprema of directed subsets. So it is so-called continuous. Vice versa, if you take a function which between two domains, which is continuous, then the inverse image preserve finite infima, so arbitrary infima and finite suprema. So, and this is the so-called categorical duality due to Lawson and I believe Henrik Hoffmann. So it is in the references. Okay, now let me say that we have been asking, okay, what we have considered maps that only preserve finite suprema. What is required for preserving also infinite suprema, so for being complete maps? And we found a posteriori that that a map, okay, is that a map which is continuous between continuous domains. Its inverse image is complete. So, in particular, what is the point? It preserves arbitrary suprema. Okay, if and only if this map preserves the way below relation. So after this, the proof is not difficult. So after having found that, we tried to understand if this was already in the literature. We found something that it is due to Hoffmann and Stralka. Okay, but with a few remarks, you can adapt this result by Hoffmann-Stralka to obtain exactly this. But we arrived to this after discovering that this preservation of the way below relation, it is very important. Okay, how? Okay, let's come to complete congruences. Okay, so in frame theory, a point is just of a frame is just a mid-prime element. Let me switch to the dual perspective. I consider joint prime elements of a completely distributive lattice. Okay, and let me call the points vet. Okay, what you can do is, given a set of points, you can say that two elements are equivalent if and only if they are above the same points in this set. And this will give you a frame congruence, better, a dual frame congruence. Conversely, what you can do, you can take a quotient of a completely distributed lattice such that the quotient is a dual frame, which is co-spatial, which has enough points. Okay, and this will be induced by a subset of points. Okay, and well, you can play a game. Okay, give me a set, construct a quotient, give me a quotient of this kind, construct the sets, and you will obtain even a bijection. And in many cases, in particular for the complete distributed lattice that I'm interested in, this is a bijection, so I can establish bijection between taking dual frame congruences in that are co-spatial and subset that are closed under suprema. Okay, this is not general this is not general, so one can find counterexample to this bijection. Okay, so okay, let me tell you what is an exterior point in a continuous domain. By duality of Lawson duality, I consider a continuous domain, okay? And in this continuous domain, I will say I want to take a downward closed subset, but I say that a subset is closed only if it is closed under directed suprema. I don't want to close it under downsets. So it is a variant of the Scott topology. Okay, so I consider by the Hoffmann-Lawson duality subsets that are closed under directed suprema. Okay, and I say that a point is exterior if I can find another point which is well below this point S, such that the elements that are above this set and well below S, intersection this set is empty. Okay, and if a set has no such exterior points, then I call it quasi-regular. Okay, so what's up? If I have an exterior point, it belongs to the frontier, but not conversely. So here it's here this point is exterior, so I can find a point X well below here, and this thing. So okay, here I'm considering. Okay, let me explain. S is the union of these two segments. Okay, and this is an exterior point of this because I can find this X and yes.
I'm sorry to interrupt you. I just wanted to tell you that you have 5 minutes from now.
Okay, good to know. Okay, and here it's an example of a point in the frontier which is not exterior. So, and then the point is that you have a subset which is quasi-regular, so with no exterior points, if and only if the inclusion preserves the well-below relation. And so the inverse image of the inclusion preserves arbitrary suprema. Okay, so this is the way that we characterize complete congruences of completely distributive lattices. Okay, so here what I find nice is that this notion of exterior points put everything together, okay? So we could have a dual frame homomorphism for a completely distributive lattice. However, you could end up in something which is co-spatial, but it is not completely distributive, and or you could have something which is completely distributive in the quotient, but the quotient map might not be a complete map. Okay, so this quasi-regular subset characterize that. Okay, let me tell you what we did more than that. So we observed that the quasi-regular subsets are closed under unions, but not necessarily under intersections. But there are nice properties. So if so you can define the interior, so the greatest quasi-regular subset, which is included in a given one. So this gives you an interior operator. And this interior operator sends closed sets, subset to closed subsets. And it satisfies essentially these properties that essentially states that, okay, if you take the dual operator on open subsets of P, where P is a continuous domain, then these open subsets form a frame, and this closure operator acts as a nucleus. The conclusion is that if you take this complement of quasi-regular closed subset, call them quasi-regular open, okay? This, it is a frame, okay? And then you can state, okay, my congruences are, the poset of my congruences are bijectively, there is a dual correspondences with, okay, they form a dual frame. Okay, so let me go ahead. We went on and remark that we could construct a quasi-regular subset that it is not regular open, okay? And this, according to a standard argument, shows that this is not a Boolean algebra. And then we went to look at this, okay, at this continuous domain and the quasi-regular subsets open, and we observe that there are no points, no copoints, one of the two, so in particular cannot be a completely distributive lattice. So it is something, but we do not know exactly what. Okay, so let me tell you also what we went back to our QOV, okay, and we considered what happens concretely, okay. Here there is my closed subset, its complement, it's open, and how acts the congruences. So I take a path and I can deform it to its least element via a directed homotopy. Well, here in the reverse order. And similarly, I can deform it via a direct homotopy to the greatest element of its congruence class. Okay, what I draw here, okay, it includes these blue, black lines, meaning that this is a quasi-regular open, okay? If I don't take this blue line, what I can do with the same path, okay, I can identify that going down, but I cannot go up because I don't have a greatest element. So essentially what we did is to make precise this intuition between direct homotopies and well, call them frame congruences, dual frame congruences in this case. Okay, so the original objective was to climb in higher dimensions. Okay, so this is still, so you can have paths in a cube of dimension n, not just of dimension 2. And you have a nice lattice structure that we worked with Maria Joao, who's there. And we would like to understand, okay, what happens in high dimension. We don't have answers for the moment, but we felt that it was needed to set formally the intuition of what happens in dimension 2, because everything is based on the algebra in dimension 2 that then we can lift in some way to higher dimensions. And I don't know how many minutes I went over.
Okay, so first of all, we thank the speaker for the nice talk. So thank you very much. And we have our round of silent applause. And now we have time for a couple of questions. So if someone wants to ask a question, I actually have one, but first the others in the audience. Is there anyone? Okay, I will ask mine in the meanwhile because I'm not sure there are questions. Okay, meanwhile, I will ask mine. So, can you say a bit more about these applications in concurrency? I don't know much of concurrency theory, so it's just a keyword for me. What kind of applications are you talking about?
Okay, so okay, I don't know if I can, how can I probably should stop the sharing and share instead a screen, no? Okay, so you have the Swiss flag, something like that. You have your two-dimensional cube. So you think that there is a process that develops along this axis, this process that develops along this axis, and then there is the Swiss cross. So essentially what happens is that what we are modeling is there is a common resource that cannot be taken by both at this interval of times. Okay, so if a path goes here, then well, so if the common path, okay, which is the development of the two, okay, ends up here, then the process ends up in a deadlock because they require both the two of them the same resources, and this resource can accommodate just one of the process, and then the process just gets stuck. So the locks in computer science are modeled like places, interval of times where only one process can enter. Okay, they cannot enter the two processes at the same time. Okay, so what they do is at some point they take this geometric shape, okay, with this hole, and they consider this well, a fundamental category of this kind of surface, and they classify the behavior of a concurrent process according to the fundamental category of the overall process. Okay, now Cameron is not there. He's desperate, and I'm sure he would say much more about this. Okay.
Okay. Um, thank you. And unfortunately, we don't have time for another question. So I don't know if we have another one, but we cannot handle it. So